Hello, here is a numerical based on parallel resonance. Okay, so this particular question I have taken from VTU question paper directly from December 2019. Okay, so as you see, the question is derive the expression for the resonant frequency of the circuit. The circuit here is parallel circuit. Also show that circuit will resonate at all frequency if RL is equals to RC is equals to root L by C. Okay, so how to find resonant frequency? We already know that I have done in the last video for series. So now I'll be focusing on this particular part. Okay, so since this is a parallel circuit, instead of writing the expression for impedance, let us write the expression for overall admittance. Y is equals to, let me write this particular branch admittance as YL plus the second branch admittance as YC. Okay, so what is YL? YL is 1 by RL plus JXL. Correct? There is a RL in series with the inductive reactance XL or inductor L. So inductive reactance XL I have written. Plus YC is 1 by RC minus JXC. Remember, whenever you are writing capacitive reactance, please do write it as minus JXC. So this is your overall admittance. Okay. So now what we are going to do? We do not want imaginary term in the denominator, correct? Because it is going to make our calculation difficult. So what I'll do? I'll multiply and divide by conjugate of complex conjugate of this one. So by then what I'll get? RL minus JXL here, RL plus JXL multiply by RL minus JXL. Similarly here, multiply and divide by RC plus JXC. Here, RC minus JXC multiply by RC plus JXC. Okay, so this one you see, it is in the format A plus JB into A minus JB. Okay, so we usually have A plus B into A minus B equal to A square minus B square, correct? So here B will be J into XL. J square is minus 1, minus into minus plus. So directly I will write in the next slide. So we get the value as Y equal to RL minus JXL divided by RL square plus XL square plus RC plus JXC divided by RC square plus XC square. Okay, you see the same thing I have written. Okay, so now what I'll do, I'll just separate the real term and imaginary term of this admittance part. So let me consider it as equation 1. So real time is 1 RL by RL square plus XL square plus one more is here RC divided by RC square plus XC square. Next plus I will write imaginary part. Since I have written plus here, I'll take XC first. RC square plus XC square minus XL divided by RL square plus XL square. Okay, we already know that at resonance, network will be purely resistive. Correct? At resonance, network will be purely resistive in nature. But here it is not just resistive, it includes some capacitive inductance, sorry, capacitive reactance, also inductive reactance. But at resonance, what we are going to do is we will consider imaginary part to be equal to 0. At resonance, imaginary term or imaginary part of this particular expression 2 will be equal to 0. Okay, so now that part I'll be writing as XC by RC square plus XC square minus XL divided by RL square plus XL square is equals to 0. So now what I'm going to do? I'm going to write it as XC by RC square plus XC square equal to XL by RL square plus XL square. I'll write here XC by RC square plus XC square is equals to XL by RL square plus XL square. Okay. Now, if you want to get the resonant frequency of this, very easy way is what? You just take up all this XC and XL square terms together, RC, RL square term either to RHS, and then XC, you write it as 1 by 2 pi FC, XL, take it as 1 by 2 pi FL. At resonance, we will take usually it as F naught, and then yes, you will get the value of F naught. But as I have mentioned earlier, we are interested in considering if RL equal to RC equal to root L by C, then it says that particular circuit resonance throughout all the frequencies. Okay, so that's what I'm going to do now. So in this particular equation, I will take RL equal to RC. Okay, so let me write it as XC divided by, sorry, not XC divided by, here XC is already there. I'll multiply this with RL square plus XL square equal to XL into RC square plus XC square. Okay, so now here I'll take RL equal to RC. XC, I will write it as 1 by 2 pi FC RC square plus 2 pi FL whole square. Similarly, here I can do that 2 pi FL RC square, since I have considered together 1 by 2 pi FC whole square. Okay. So now what you can do, you can either take out RC square terms together somewhere here. What I'll be doing, 1 by 2 pi FC RC square. I'll bring this here minus RC square into 2 pi FL equal to this multiply by 2 pi FL. So what remains is 1 by 2 pi FC L by C. I will write it as C 2 pi FL multiply by 1 by 2 pi FC. 2 pi F gets cancelled. What remains is only L by C square into 1 by 2 pi F. Okay, so that's what I have written here. Minus, here also I'll multiply 2 pi FL square into 1 by 2 pi FC. What remains is 2 pi FL L by C. Okay, so now I'll take all the common terms out. Let me write it here. RC square 1 by, I have to go back to the slide, 2 pi FC minus 2 pi FL is equals to, see here, 1 by 2 pi FC minus 2 pi FL, L by C I'll take as common. Okay, so L by C 1 by 2 pi FC minus 2 pi FL. So these gets cancelled out. The equation you see RC equal to root L by C. So already we have considered RC equal to RL. So RL also will be equal to L by C. So in case if RC or RL is equals to root L by C, this particular network will resonate for all the frequency. Please remember. Okay, so that there will not be any resonant frequency or something when RC equal to RL, because this particular circuit resonates for all the frequencies. So that's what we were supposed to find from this particular numerical. Hope you understood. Thank you.